Hello guys, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of electrical circuit. So at this chapter, I thought it would be better to again one step back and try to have some conversation related to the very important section of electric circuit, which is resistance. Because so far we learned so many things about how we can connect them, series, parallel, how we can measure the resistance itself, how we can measure the voltage, current, or anything related to the power dissipation, and all fantastic stuff. But yet we have to make sure our knowledge is solidified. So that's why I dedicate this chapter, which is, I can say, is a subsection of some kind of our main goal in order to reach to complete understanding of electrical circuit 1 and 2 to resistor itself, how we can read them and see a couple of examples that how we can put them side by side in order to find the total resistance, so on and so forth. So stay with me, we are going to talk about the very interesting stuff. So at this point we are going to master the resistance itself from color codes to complex circuits, and I will tell you what do I mean by color codes itself. So at this point we are going to have the practical guide in order to calculate the series, parallel, and mixed resistance itself. As we know, when we do have the series resistance, it means that all of them are back to back or connected to each other. On another hand, when you have a parallel, it means that both of them are going to be connected in parallel with 2 points with each other itself. So let's talk about it. The very first thing you have to know is, again, as I told you, the role of resistor. Why we use the resistor? Again, the resistor is by itself or by nature something that is going to consume some power. As you all know, we are going to have something we call as a voltage drop. So maybe some of you again ask why we're going to use the resistance again? Because obviously if we are going to put it in a circuit itself, we are going to lose something. And I told you that sometimes we need to control the amount of current that gets inside our load itself. At this point, imagine that I do have a circuit, and this circuit contains 3 important parts. The very first part is the source. That source should be connected to my LED or lamp in order to make that guy on, right? In the meantime, I know for a fact that my LED or lamp only can handle maybe milliamp of current itself. What should I do? Either I have to reduce this voltage, which is sometimes is impossible because I do have the constant voltage, or I can put a resistance beside. By having this resistance and based on the Ohms law, I'm doing what? I'm going to increase this resistance itself and also reducing the total current itself or the total current. So I'm sure that my LED is not going to have or tolerate that much of a current itself, and everything is going to be safe. So again, the resistor's primary job is to limit the flow of electrical current. It also creates specific voltage drops within everything in the circuit itself, and its value is measured in ohms, something we know. Again, the fundamental relationship was the relationship between I, V, and R itself. As we all know, this is something like the triangular, that V and I and R, we can get some help from that in order to convert one to another itself. So let's talk about a very interesting topic, because we talked about the resistors, but we didn't talk about it, the physical shape of resistor itself. The physical shape of most resistor that you would see in the lab would be like this. You see that we do have color. It means that this circuit is color coded, or most of the time has 4-band color itself. What is that? So the anatomy of a 4-band resistor, it would be like this. We do have the first color. We call it as first significant digit. By the way, something happened. And by the way, this is the first one, should be that black guy over here. And the second band should be this blue guy. The second band is the second significant digit. The third band is the multiplier, how many zeros we have to add, and the final band is the tolerance. How we can read that? It means that I do have something like this. If I would like to see how much my R is, I have to have something like this. AB times or multiply 10 to the power of n, everything multiplied by the tolerance percentage. A is the first digit. It could be from 0 to 9. Based on the color, we do have a table for that, and it could be from something from 0 to 9. B, same scenario. N, again, is going to be a number based on the third color that I have. And finally, this guy is going to be based on my tolerance band. So The golden rule of this reading is that the very first part is at the very we should start the reading, because sometimes we do have this one, sometimes we do have this side. In order to make sure that we are reading the right side, we can use this golden rule. The golden rule said that if you would like to read the resistor based on the color coded and then put it inside this formula, is that start reading from the side where the bands are grouped together. As you can see over here, the bands are grouped together. The tolerance band often is gold or silver, so typically has a larger gap before it. It means that we do have this gap before the grouped and the final one as the tolerance. So right now, let's talk about the colors. Each colors means something, and it doesn't necessarily mean that you have to memorize it. You can have it as a reference, but right now, black means 0, brown means 1, until the end. Why we use that? Again, we are going to use that to put it inside this specific formula that I was talking about. By putting there, you make sure that you can read your resistance without even measuring it by color coding that. So let's talk about the case. Imagine, just before that, the very important part is understanding the multiplier and tolerance bands. As I just told you, in the formula we had a multiplied by 10 to the power of n, which is going to be multiplied based on the color. I know how many zeros I have. Everything multiplied by what? By 5% or 10%, that we call it as tolerance band. So the common multiplier that we do have, the band number 3, which is n guy, is going to brown. It means that 1 0, red 2 zeros, orange 3 zeros, yellow 4 zeros, and green could be 5 0. So we have to look for that some kind of specific tolerance band. It means that we do have 5% or 10%. What is that? Means that the number you're reading right now probably is going to have 5% to 10% of error with the actual value. This is the number that you're going to read from the resistance itself, but it probably has going to have 5% or 10% of error itself. So that's the case. Let's decode this one. Let's decode a 330 ohms resistor. We know 330 ohm resistor should be something like this. 33 times 10, and we can consider the 5% or 10% of tolerance. Right now, we just taking care of these first 3 band. So the very first color should be what? The very first color should be 3. What was 3 was what? Was orange itself. The next color should be again orange. So we do have orange. The next color should be only 1 0. We know it from brown. It's going to contain 1 0. So we do have at orange, brown, and finally could be golden or some kind of silver itself. Even if we didn't know anything about the numbers from the beginning, we just can look at the colors. Orange means 3, brown means 10, and this guy means 5%. 33 times 10 is going to give me 330 ohms itself. What about kilo ohm? So for the kilo ohm, again, we do have these guys as grouped. We do have the 5%. So I do have brown. Brown means what? Brown means the first number. So that guy is 1. Black is the second number. This guy is 0. Red is the third number. It means that guy has 2 zeros in itself, and this guy is 5%. So right now, multiplied by 10, 1 and 0 is going to be 10. By 100 is going to give you 1K itself. What about 5.1K resistor? We do have as green, brown, red, yellow, the golden, sorry. So we do have it as green. Green means that 5. And then we do have the next one as brown, means 1. Then we do have the red, means that 2 zeros. And if you just do this calculation, you have 5.1K. The very important warning would be that this is common trap. The red band means 2 as a digit, or by 100. But this guy is a multiplier. A band's meaning depends entirely on its position. So be very careful about that one. If red is over here, means that 100. If red was something, for example, here, and you have it as red, this guy means what? This guy means 2. So these are 2 different things, so be very careful about that. Right now, we learned how we can read the resistors, and that was so fun. So let's talk about the first rule of assembly. Means that resistance in series. Actually, we know that, right? When you have the series, means that those things, or all of your resistors are going to be side by side connected to each other. They only have one common connection spot. And also, we know for a fact that the I total is going to be I1, I2, and I3. It means that it's going to be the same for all of them. So R total is R1 plus R2 plus R3, or if everything that you had side by side. The mini example, 100 ohms, 220, and 330. The only thing you have to do, add them up. 650 is going to be your final answer. And we all know about the sanity check means that your final answer should be what? Bigger than the biggest resistance that you have in your total package itself. Then we had the power resistance. For a power resistance, we know that two resistance, we have R1 and R2, are going to have two common spots, right? The first common spot, the second common spot. How we can find the R total? It was reciprocal. It would be 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3 and etc. If we do have a common case that only two resistors would be there, we know this formula. R1 times R2 divided by R1 plus R2. What would happen if I do have 220 and 330? Multiply, divided by adding up, you have 132 itself. So the most important check, total power resistance is always, guys, going to less than the smallest individual resistance. It means that 132 is going to be right. Why? Because it's going to less than 220 and less than 330. So let's calculate the series resistor. At this point, I do have 10, 100, and 220. How I can do that? Adding them up. 10 plus 100 plus 220. If you do that one, you have 330. Is that right? Yes, because our total is going to be bigger than all of those numbers. What would happen if I would like to calculate the parallel part of 1K and 2K? As we all know, we have to do this what? We have to R1 times R2 divided by R1 plus R2. If you do that one, make sure when you do have K, or most of the time we use it for K, by the way, so because it's easier. When you have meg, it would be a little bit challenging. Try to convert your K to ohm itself. We know that 1K is going to be 10 to the power 3. 1 meg is going to be 10 to the power 6. 1 milli is going to be 10 to the power negative 3. Is that the case? So we do have 1000 times 2000 divided by 1000 plus 2000. We are going to have what? We are going to have this number. Is that right? Yes, because this guy is less than all of those numbers itself, because we do have the parallel section. So what about the time that we do have the mixed condition? What does that mean? It means that at this point, I do have two resistance. They are in parallel. On another hand, if I find the R total of these guys, obviously is going to give me one resistor. This guy is going to be in series with another one. Right now, we do have the mix scenario, the mixing of series and parallel. What we should do is easy, step by step. First of all, try to find the R total for this guy. What is the R total? Is 100 times 220 divided by 100 plus 220. It's going to be this value. Then we have to move to the next part. It means that we have to add it with 330. So we do have this guy as our final answer. Simple as that. Let's see another example. At this point, I do have two resistances side by each other, 1K and 2K as we had. And right now I do have 5.K in parallel. What I should do, the very first part is the branch. So we will talk about what does that mean by branch, but imagine the branch is just like a path. This branch A and branch B. Branch A should be the accumulation of 1K and 2K in series. So if you find that value, that guy, it would be 3K, right? Actually, this is not, 300 K ohm. Then I do have my 3K, about 5.5K, do this calculation based on this formula, and you have your final answer. R1 times R2 would be 300 times 5100 divided by 3000 plus 5100 itself. If you do that one, you have this one as your final answer. Is it right? Yes, because this guy is smaller than the smallest resistance in parallel itself. What would happen if we do have two parallel blocks in series? Again, the story is not that hard. The very first thing you have to do, find the things you are parallel of 10K and 100K. Then you have finding the parallel of 1 meg and 100K. And then if you find R total, for example, it is RT2 and this guy is RT1, just add them up. Simple, right? So what is R1? R1 is 10K times 100K divided by 10K plus 100K. You do have something like this. Then step number 2 is to calculate the block number 2. It means that I do have 1 mega ohm right now. So 1 mega ohm means 1 million ohm or 1000 kilo ohm. At this point, I do have 1000 kilo ohm and 100K. So I'm going to do this multiplication, again, do this addition, and finally, I'm going to have this one. What I should do at the end? I have to add these two guys up. After adding them up, I do have my final answer, which is 100K itself. Simple, right? So let's talk about some checklists. Let's talk about some problems that you have to avoid. The very first thing was about the parallel sanity check. What was that? It means that when you find the accumulation of parallel resistances, make sure to check it with the smallest one, because your final answer after making them parallel should be smaller than the smallest number.
Position is everything. Another thing that you have to know is going to be that about the color coded. When you're talking about the color coded or color digits, you have to make sure when your color is at multiplier, you have it as 10 to the power n. N could be any number. But when your number or color is at digits, that guy should be just normal digits itself. Try to keep your units clean, okay? Have the kilo ohm, try to make it as 1000 ohm when you have the mega ohm. 1 million ohms would be a little bit challenging, but you can convert it to kilo ohm. Most of the time, mega ohm comes with another kilo ohm. So you can simplify that, but still make sure that you're completely fine with everything, because we don't want you to have any problem. And finally, one block at a time. When you're faced with a mixed circuit, always simplify it in stages. Reduce each parallel or series block into a single equivalent resistor before just moving on.
So at this point, and at this some kind of section, which was somehow a very mini section or mini chapter, I was trying to talk about one important thing, which is the color-coded resistance, how we can read them, then how we can have this mixage of series and parallel resistance itself. Next part, we are going to talk about in more detail, but probably we are going to have a simple lab. And that lab, we are going to talk about how we can use the breadboard and how we can some kind of apply the resistances there, how we can connect them in series and parallel, and how we can have some voltage and current itself. So stay tuned. It's going to be so much fun. Don't forget to like and share and comment. It would be so helpful for me. Have a super great day, night, whatever. See you around.